In this problem, we are asked, a uniform board supports two children, one weighing 500 newtons and the other weighing 340 newtons. The support is under the center of mass of the board, and the 500 newton child is 1.6 meters from the center. Where should the 340 newton child sit to balance the system? So we're going to first draw a picture of the situation. Okay, so we've got a board supporting two children. It's kind of like a seesaw. Okay, and the support is at the center of mass of the board. So we're going to say the board's uniform, so it's pretty much the center. Okay, and there's one child sitting on this board, and that child has a weight of 500 newtons. Then we've got another child sitting on the other side, and this child has a weight of 340 newtons. It also tells us that the 500 newton child is 1.6 meters from the center, and it asks where should the 340 newton child sit to balance the system. Okay, so this problem, if we want this to be balanced, we need the board to not rotate clockwise. We need it to not rotate counterclockwise. So we need it to not rotate, okay? If an object is not rotating, then it is in rotational equilibrium. It could also be rotating at a constant velocity, but in this case, they want it to be balanced. So we want it to be not rotating. And if it's not rotating, that means that the net torque is equal to 0, because if there was a net torque, it would cause an angular acceleration, it would cause a rotation. Okay? So we need the net torque to be equal to 0. Well, we've got our picture. We have an idea of what we're going to do. We also need to just go ahead and write down these givens a little more specific. So let's go ahead. This is the weight of the first child. Weight is also known as the gravitational force. So this is the gravitational force of the first child. I'm going to say 1 there for first. This is the distance the first child is sitting from the point of rotation. So we're going to call that D1, 1.6 meters. Okay. Other side, we have the gravitational force of the second child is 340 newtons. And we know that we are trying to find the distance that the second child is from the center. Okay, again, we know the net torque needs to be equal to 0. I know that if I apply a force at a distance away and it's not an angle of 0, I'm going to create a torque. So there's going to be a torque created by the first child, okay? And there's going to be a torque created by the second child. These two torques must add up to 0, okay? So what does torque, how do we find the torque? Well, we know that torque is equal to the force times the distance times the sine of the angle. What angle? Well, that's what we're missing from our givens. So I need to find the first angle. And remember, the angle is the angle that starts at the point of rotation, goes to the force, and goes in the direction of the force. Well, if this is balanced and not rotating, this will be a 90-degree angle. So theta 1 is 90 degrees. Similarly, theta 2 is going to be 90 degrees. Another consideration that we need to take is this. This torque, child 1's torque, will cause the object, the seesaw, to rotate counterclockwise. That is the positive direction. This torque will cause the object to rotate clockwise. That is the negative direction. So we need to take that into consideration as well, similar to when we used to look at our free body diagrams and decide which forces to be positive, which forces should be negative. So let's go ahead and start substituting in. So I've got force 1, distance 1, sine of theta 1, plus negative force 2, distance 2, sine theta 2 equals 0, because again we are in rotational equilibrium. So now I'm going to go ahead and substitute my numbers, and I've got 500 times 1.6 times the sine of 90 plus negative 340 times distance 2 times the sine of 90 is equal to 0. Simplify the first term, I get 800. Simplify the second term, I get negative 340 d2, and that still adds up to 0. Subtract 800 from both sides. Negative 340 d2 is equal to negative 800. Divide by negative 340. The distance that child 2 should sit from the center is 2.35 meters. Okay, if we look at this, okay, child 1 is significantly heavier than child 2. Okay, to make up for their lack of weight, they need to apply their force further. So they need to sit further away. If you look at this, they did. They sat 2.35 meters away versus the heavier child sitting closer at 1.6 meters away.